Hello! Today you are going to learn prime factorization. Prime factorization is the process by which we split a number, a natural number, into its component pieces. And its component pieces are primes, prime numbers. The prime numbers are like the atoms of the value. They can't be split any further and still be natural numbers. So we're going to take numbers and split them into its primes. And every number can be split into primes unless it is itself a prime, in which case it can't be split because it's already a prime number. Okay. And interestingly, every number can only be split into primes one way. No matter how you go through the process, you're still going to end up with the exact same prime factorization. And I will demonstrate that. All right. There are actually two ways to do this. There's factor trees, and then there's a factor ladder. I will show you both. I prefer the factor trees, but that might only be because I am more familiar with it, and it has a tiny bit more creativity to it. But factor ladders are perfectly appropriate also. Completely appropriate. Okay, so we'll start with a number. I am going to start with the number 30. I like 30 because it has a number of different ways. Remember the prime numbers. I'm just going to write them down off to the side. 2, 3, 5, 7, 11, 13, 17, 19. Always very useful. By the way, I can tell that I'm not going to use 17 and 19 because they're more than half of 30. I'm only going to have to use 2, 3, 5, 7, 11, and 13, and I'm not even going to have to use all of those. All right, so 30. Well, how can I make 30? What times what is 30? Well, 3 times 10 is 30. So I'm going to put 2 lines here. This, by the way, is factor trees. 2 lines here, and I'm going to put 3 times 10. Okay, now 3 is a prime number, so it is not going to be split up again. So I'm just going to put a vertical line underneath it. It's going to stay 3 because it's already prime. 10 is 2 times 5. So it gets split up, and it's 2 times 5. And 3 is just 3. Now, all 3 of those are prime numbers, but the prime factorization is not quite finished. You want to put them in order, least to greatest. 2 times 3 times 5, and that is the prime factorization for 30. Notice, 2 times 3 is 6, 6 times 5 is 30. But commutative property, 2 times 5 is 10, 10 times 3 is 30, 3 times 5 is 15, 15 times 2 is 30. Doesn't matter what order you do it in, it still makes 30, and those are the prime numbers, 2, 3, and 5. I'm going to do another factor tree using 30, and the only reason I'm doing this is I want to show you that it will come out to the exact same prime factorization. The only prime factorization for 30 is 2 times 3 times 5. But there's another way to get there. So 30 is also 5 times 6. So 5 is prime, bring it down. 6 is not. 6 is 2 times 3. So notice it is still 2 times 3 times 5. The exact same prime factorization as we got before. So that's the idea of factor trees. Let's do another one just for practice. Okay? So let's try the number, I don't know, how about 42? 42 is 6 times 7. 6 is 2 times 3. 7 is prime. They are already in order, so 2 times 3 times 7, and then circle it. When you're doing your work on prime factorization, make sure to write it in order from least to greatest, put multiplication symbols between them, and circle it to say that's the answer, that's the prime factorization. Interesting so far. Let's try something a little bit bigger. Let's try 350. 350 I think of as 35 times 10. 35 is not prime. 35 is 5 times 7. 10 is not prime. 10 is 2 times 5. So the prime factorization, those are all prime numbers, so we're finished. The prime factorization of this is 2 times 5 times 5 times 7. And yes, you do want to list the 5 twice, otherwise we don't get 350. If I only put 2 times 5 times 7, that would be 70. It would not be 350. There's a way to write it using exponents, but we're not doing that right now. So that's using factor trees. As I said, I like that, but there is this other method called factor ladders, I believe. It might have a different name. I think of it as a ladder. So we start with our number. Let's try 350. And I look at it and I think, is it divisible by 2? You always start with 2 because 2 is the smallest prime number. So we'll divide by 2. 2 goes into 3 once with 1 left over. 2 goes into 15 7 times with 1 left over. 2 goes into 10 5 times, no left over. By the way, if there was any left over, then we know it's not 2, but we knew it would be 2 because it ends in a 0, and we know the rule is 0, 2, 4, 6, or 8. So, ends in. See, I made that same mistake. Its ones place is 0. Doesn't end there, it continues forever in the decimal places, but its ones place is 0. Okay, so we did the 2, we have the 2. 5 is there, 5 is not divisible by 2, we're done with 2. Let's try now 3. Well, let's do the trick for 3. 7 plus 1 is 8. 8 plus 5 is 13. That's not divisible by 3. Let's try the trick for 5. Is the ones place 5? Yes. So that means it's divisible by 5. Oops. I just put the division bracket. I'm using an upside down division bracket. That's the way I learned how to do it. 5 goes into 17 3 times with 2 left over. So I put the 2 next to the 5. 5 goes into 25 5 times, no left over. We knew that would happen. Okay, are we done with 5? No, because it still has a ones place of 5. So we'll divide again by 5. 5 goes into 35 7 times, no left over. So we know that we're done. Here is the prime factorization. 2 times 5 times 5 times 7. 2 times 5 times 5 times 7. And notice, it's the same as we got before. It's just a different way of doing it. Both ways are correct. I want to try another one just to give you enough practice, enough ability to see another example. Let's try 96. Okay, so division bracket upside down. Does 2 go into it? Is 2 a factor? Yes, 2 is because it ends in a 6. So 2 goes into 9 4 times, 1 left over. 2 goes into 16 8 times. Does 2, now we're not done with 2 because it still has the 8 in the ones place. So 2, some people, by the way, like to step back their division brackets. It's fine if you do, it's fine if you don't. 2 into 4 is twice, no left over. 2 into 8 is 4 times, no left over. Are we done with 2? No, because we still have a 4 in the ones place. Divide by 2. 2 into 2 is 1. 2 no left over. 2 into 4 is 2. Are we done with 2? No, because it still has a 2 in the ones place. 2. 2 into 12, 6. Still not done with 2. 2 into 6, 3. So now we're done because 3 is a prime number. We can't split it up anymore. The prime factorization for 96 is 2 times 2 times 2 times 2 times 2 times 3. And that is the prime factorization. I've shown you 2 different ways to find prime factorization. I've shown you the ladder method and the factor tree method, and I've demonstrated that it doesn't make any difference how you organize it. you still will end up with the exact same prime factorization. Every number only has one prime factorization. It's made up of prime numbers, and you have to start with a natural number. By the way, if you wanted to start with an integer, one of the factors would be -1, and then it would be negative, and then that's fine. But these are all natural numbers, so we won't be dealing with negative numbers. Find each prime factorization, show your work, make sure it all makes sense. Any questions?